All right, hello y'all. Today we're going to be talking about molecular geometry. So just remember a quick rundown. Molecular referring to molecule, meaning a covalently bonded compound. Whoops, can't spell today. And geometry referring to the shape. So these covalently bonded compounds make a bunch of different shapes. So we're just going to talk about what makes the shape. And to do that, what I want to first do is just look at a general Lewis dot diagram. And so the one I'm going to look at is starting with ammonia. Nh3. So a couple terms we need to remember are electron sets, which are going to be any bond or lone pair. Up next, that brings us to the next term, lone pair. That's going to be an unbonded pair of electrons. And then lastly, we're going to look at a bond, which is just a bonded pair. And it can be a single, double, or I don't know, I was going to do three, triple covalent bond. So if I do a quick highlight, I'll use green to highlight my bonds. I'll use blue to highlight my lone pair. And I'm not really going to highlight in gray. I'll just use red to highlight my electron sets, which is just pretty much everything. And one final key component about molecular geometry, and I'm going to put this in red and put a little star, is we only look at the central atom. We don't really have to look at anything else. So we're only looking at the central atom. So in this case, our central atom is going to be nitrogen. So nitrogen here has, this example, we have, I'm going to put down here, we have 4 sets, 1 lone pair, and 3 bonds. And so I know that this shape is going to be, this shape here is going to be pyramidal. Sorry, I was going to say something else, but it's going to be pyramidal. And if you look at it in 3-dimension, basically it's going to look like our nitrogen standing on kind of a pyramid of hydrogens. And I usually fill in this bond to kind of reference that's actually behind the page, coming out of the back of the page. Now, what we're going to be using is actually a chart. So I'm going to go ahead and just come down here to a whole new page on my iPad just so I can kind of start fresh. And we're going to call this the molecular geometry chart. The most important thing about the chart is we're going to look at the electron sets. Then we're going to look at the number of bonds. And then we're going to look at the number of lone pairs. Something else that's always good to know is the bond angle, which is the shape that these bonds make over here. So the shape, the angle between the 2 hydrogen in degrees, usually some angle. And then lastly, we're going to look at the name. Every shape has a name and we're going to learn them. So I'm going to go ahead and make my chart. Let's try something cool. How about a nice little purple? And maybe I'll just go ahead and duplicate this a couple hundred times. Then let's actually do this the fast way. We may not need this many lines. I'm just trying to get a little bit ahead of myself. This is going to take me a second. Feel like sometimes I should get these charts ahead of time, but you can just skip ahead because this is YouTube. Unless it said puzzle, then I apologize and you can't skip ahead. So now that we have this, let's just go ahead and get started. So the first thing that we're going to look at is when we look at any atom, the most that we're possibly going to have that we'll at least deal with is carbon, which if we look at carbon real quick, I'm going to do it right here. It's got 4 valence electrons, and so we know it can make 4 bonds. So the most amount of sets we're going to have is 4. Again, if you look at something like maybe chlorine, you have 1 valence electron, so 1 bond, but you also have an electron set up top and on each side along with the bond. So the most sets we're really going to be dealing with, at least in this chemistry, is 4. So if we have 4 sets and 4 bonds, like in this carbon, maybe we say bonded to a couple hydrogens in what's known as methane, or CH4, we're not going to have any lone pairs. You can see right here that we have no lone pairs. Those are all bonded. This bond angle in 3 dimensions is actually 109.5 degrees, and we call this tetrahedral. Hedral referring to like a 3-dimensional shape, and tetra meaning 4. So it's got our 4 bonds. It's at an angle of 109.5 tetrahedral. So next thing we'll look at is, honestly, it's our picture of ammonia, Nh3. N has 1, 2, 3 bonds to hydrogen and 1, 2 electrons, which form a lone pair. So we have 1, 2, 3, 4 sets again. But this time we have only 3 bonds and 1 lone pair. Bond angle is still 109.5. All we kind of do is just remove 1 hydrogen off the top and change it to a lone pair. And as I said before, this is going to be pyramidal. All right, so we're going to just kind of blaze through some of these. Our next one we're going to look at, again, is going to be 4 sets. We'll look at one of my favorite substances in the world, dihydrogen monoxide, or H2O, water. And if we count this out, we have 1, 2, 3, 4 sets, but they're split evenly, 2 and 2. So we're going to go 4, 2, 2. You guessed it, 109.5. Little PS, water is a bit different. The bond angle is going to be actually a bit tighter. Water is special, but we don't have to worry about that right now. And we'll call the shape bent. It's called bent for pretty obvious reasons. It's kind of, well, bent. All right. The last one we're going to do, normally I might do something like HCl. So that would be this guy down here, where we have 4 sets, 1 bond. But anything containing only 2 atoms, no matter which orientation of the atoms, is going to be linear. And it's going to be a line, so I'm just going to kind of skip over that. Well, I'll do it right now. If we have 4, 1 bond, 3 lone pairs, it's actually going to be 180 because a line is 180, and we'll call that linear. All right, so moving on to 3 electron sets. How do we get 3 electron sets? Well, usually what we can do is add some double bonds, because if we look back up here, any bond can be a bonded pair, and we can have a single, double, or triple covalent bond and still call it a bond. So what I'm going to do right here is CH2O, which is a carbon with 1 hydrogen, 2 hydrogens, and a double bond to an oxygen. Now, if you remember from earlier too, I said we only look at the central atom. So we're actually going to ignore the lone pairs on oxygen, just count 1, 2, 3 bonds. And so that's going to be 3 sets, 3 bonds, 0 lone pairs. And the angle is going to be 120 degrees. At this point, it actually sits flat on a plane. There's nothing coming in or out of it. If you look at it from the side, you're just going to see you're not really going to see much. You'll see the carbon, a hydrogen, double bond to an oxygen, and there's a carbon kind of going at the back. So you kind of only see a line. Somewhere in the back there, you have a hydrogen. But on the top, it just kind of looks like this nice little triangle with 120 degrees on either side. And we're going to call this trigonal planar. Trigonal referencing that it kind of forms a triangle, or it's got three sides, and planar referencing that it sits flat on a plane. That's my kind of demonstration of the planarness. And we'll build all these as well. So up next, we have 3 bonds, or 3 sets, 2 bonds, 1 pair. You'll notice I'm just starting from the max bonds, going to the max pairs. And a good example of this might be, oh boy, I have to think about it. Oh no, I got one. A good example of this might be, nope, scratch that. NOH. And so we're going to do a nitrogen, double bond to an oxygen, single bond to a hydrogen with 2 valence electrons. And this is going to have another bond angle of 120 degrees. This angle is going to be 120, and the angle between the electron set and the bonds are also 120. So we're going to take the smallest total angle between the 2 bonds right here, and that's going to be 120. And we're actually also going to call this bent, because again, it looks bent. It's at kind of a wider angle than before. 120 is greater than 109.5, but we still call this one bent. All right, and if we really want to do 312, I can figure something out. Yeah, I might as well. 3 sets, 1 bond, 2 lone pairs. Sorry, I'm having trouble thinking of one. I guess I can just start writing and see what happens. We could do, gosh, it's so hard to think of an example when you need one. Let's do S double bond to something else that has a double bond. It's another sulfur. We'll just do S2. And again, there's only 1 bond, but there's no real central atom. I mean, that's kind of why the two model also breaks down, because we don't have a center. But either way, the set bond angle is going to be 180 degrees. So we'll just say 180. Again, that's going to be linear. All right. So we're almost done here. Now we're going to be looking at the 2 sets. 2 sets with 2 bonds and 0 lone pairs. Well, one of my favorite examples of this is going to be CO2, carbon dioxide. We have a carbon, double bond to an oxygen, double bond to an oxygen. And again, we only look at the ones around the central atom, which is the carbon. So that's going to be 1 bond, 2 bonds. And we can say this is 180 degrees. You can even see that. We call that linear. So this is pretty much the chart that you need. Let's see. Let's see if I can zoom in and only get the chart. Right there. I want to give you a good screenshot option if you don't want to. So right here is the chart. This is everything you need to know about molecular geometry. Just count the sets, the bonds, and the lone pairs. And you can reference this chart, find the bond angle pretty simply, and find the name of the shape. So hopefully this helps, and have a great day, y'all.